Standard 6.5, word problems involving exponential growth and decay. So for all of our word problems, we're going to keep our model y equals ab to the x in mind. Now keep in mind that a is your initial value, b is our growth or decay factor, t is generally time, and y is the amount after time, also thought of as your final value. And so using this model here in this particular equation, or this particular problem, it says a population of 800 beetles is growing each month at a rate of 5%. Our initial value is how many beetles we're starting out with. So that's A, that's 800. And our growth or decay factor is what percent of beetles do we have the next time compared to the previous time. Since it's growing at a rate of 5%, it's increasing by 5% each time. We're always starting with 100%, that's the amount that you currently have. And in this case, you're adding 5% because it's increasing for a total of 105%, which converts to the following decimal, 1.05. This confirms the fact that it's growth because our b is greater than 1. Now we want to write an equation that represents the number of beetles at time t. So y equals a, which is 800, times b, 1.05, to the x, or in this case to the t power. This is your function. The second part of this problem says how many beetles will there be in 8 months? So let's take our function and let's replace t with 8. Then it's just a matter of calculation. So pull up our little calculator here and we have 800, whoops, times 1.05 to the 8th power, and that's about 1,182 beetles. Let's look at another example. So here we have your new computer costs $1,500, but it depreciates in value by about 18% each year. In this particular problem, A, our initial value, is 1,500, and B, which is our growth or decay factor, in this case it's decay because it's depreciating, it's going down in value, we're going to get by starting with 100% and this time subtracting our rate, so minus 18%. This works out to be 82%, which as a decimal is 0.82. That's less than 1, confirming the fact that it is indeed decay. So our function looks like the following. Y equals A, which is 1,500, times B, which is 0.82, to the t power. Now we want to know how much will your computer be worth in 6 years. So let's take our equation and let's put in 6 for t. Going back to our calculator here, we have 1,500 times 0.82 to the 6th power. It's going to be worth about $456.01 in 6 years. Now the last question is how long will it take before your computer is worth close to $0? And these words close to $0, that's a little tricky to interpret here. Let's go back to our equation. Y equals 1,500 times 0.82 to the t. And if we took this equation and started plugging in values for t, matter of fact, let me go to our graph, or y equals 1,500 times 0.82 to the t power, or x power. And I'm going to set up my table so it's in ask mode. And let me go to our table here. And let's try values of t. So if we put in 6, we see that we have $456.01 as we calculated in the previous previous problem. If we put in 10, oh, it has gotten to be less. If we put in 15, 76, let's put in 20, 28, maybe 30. Okay, now it's worth only $3. And 40, it's worth 50 cents. And 50, it's worth 7 cents. And 60 years, 60, it's worth 1 cent. In 65 years, it's worth, looks like 0 cents. So somewhere between 60 and 65 years. But the thing that's interesting about this problem is that if we go back and think about graphing this function, we have a horizontal asymptote here at y equals 0. It's decay. And so our graph actually never hits 0, which means this y value will never actually get to 0. It'll get really close to 0 as we saw, but it'll never hit 0. So this problem's a little bit open to interpretation. This is standard 6.5, more problems involving exponential growth